Welcome back to hypothesis testing. Done right? Part 9 of 14. In Part 8, we defined the p-value as the probability of data, this extreme assuming the null is true. Now comes the correction that matters more than almost anything else in this book, what the p-value is emphatically not. Getting this backwards is the most frequent error in all of applied statistics, so we slow down and burn it in. Here is the correction. The p-value is not the probability that the null hypothesis is true. Sam's p of 0.046 does not mean there is a 4.6% chance the rule has no edge. The p-value is the probability of data, this extreme given the null is true. The thing students want it to be is the probability the null is true given the data. These are different conditional probabilities, and swapping the two sides of the bar is a basic probabilistic error. The same error as confusing the probability of wet given rain with the probability of rain given wet. They are simply not the same number. To even speak of the probability the null is true, you would need a prior probability and Bayes' rule to update it. A p-value contains no prior and makes no such statement. It assumes the null outright and never questions it. The hypothesis is fixed, and the data are the random thing whose extremeness we measure. Reciting the correct definition until it is automatic is genuinely time well spent. This one error, more than any other, separates careful empirical work from sloppy. A second, related caution, a p-value is itself a random variable. Run Sam's back test on a fresh year of data, and you would get a different average, a different t-statistic, and a different p-value. A p of 0.046 and a p of 0.055 are practically the same evidence. The 0.05 line is a useful convention, not a law of nature, and treating it as a cliff edge is a habit worth distrusting. In fact, there is a clean and underappreciated theorem here. When the null is true, the p-value is uniformly distributed on 0 to 1. Every value is equally likely. And that is exactly why a true null still produces a p below 0.05 a full 5% of the time, which is just the definition of a 5% false positive rate seen from the p-value side. Hold onto that uniformity, because it is the seed of the multiple testing problem we reach at the end of the chapter. A small p-value from a single test is only mild surprise. It carries real weight only when it would be surprising across everything you tried. To summarize Part 9, the single most important correction in this book. The p-value is the probability of the data given. The null is true, never the probability of the null given the data. Swapping those two is the rain versus wet error. And to even speak of the probability a hypothesis is true, you would need a prior and Bayes' rule, which a p-value simply does not contain. Beyond that, the p-value is itself a random variable. A value of 0.046 and a value of 0.055 are essentially the same evidence, so the 0.05 line is a convention, not a cliff. And because a true null makes the p-value uniform on 0 to 1, 5% of genuinely dead rules slip under the line by pure luck, a fact that will come back to bite us. In Part 10, we meet a richer, more honest object than a single verdict, the confidence interval.